In the previous video, we learned how to calculate the shading factor when the surrounding environment of the PV system is considered. In this video, we will learn how the surrounding environment affects the Skyview factor. The learning objectives include understanding the importance of the Skyview factor, or SVF, in irradiance modeling, followed by a method to determine them when surrounding environment of the PV system is included. First, let's recap where the Skyview factor is used in the irradiance modeling. By now, you are familiar with the three different irradiance components: direct irradiance in red, diffuse irradiance in green, and albedo in orange. We derived expressions for these components as a function of the tilt and azimuth angle of the PV module. In irradiance modeling, the Skyview factor is used in the calculation of both diffuse and albedo components of irradiance falling onto PV modules. To calculate the diffuse irradiance, several models have been developed, each based on different principles and varying in complexity. As we have seen in the previous videos, for each of these models, one or more input parameters are used. These are global horizontal irradiance, or GHI, diffuse horizontal irradiance, or DHI, angle of incidence, AOI, and the Skyview factor, SVF. Among these, the only input parameter common for all the models is the Skyview factor. Hence, it is a very important parameter that has to be calculated in irradiance modeling. The Skyview factor, as you know, is defined as the fraction of the sky that a surface sees, and it is a function of the tilt angle of the PV module. In an ideal case, that is for a free horizon where there are no surrounding obstacles present, the Skyview factor is related to the tilt angle of the PV module according to this equation. For example, the SVF for a module placed horizontally is simply 1, while for a tilted module, the SVF decreases depending on its tilt angle, since the module sees a smaller fraction of the sky. This method is very useful to calculate the Skyview factor when the PV system is located in a free horizon condition. Let's now see how the Skyview factor is calculated when dealing with the complex horizons. When the PV system is located in a complex environment, such as an urban landscape, its surrounding environment will also have an influence on the Skyview factor. Thus, a detailed estimation of the Skyview factor has to be carried out. One available method to carry out such an analysis is the computer-aided design-enabled approach, or CAD-enabled approach. The approach enabled by CAD design is used to determine a more realistic Skyview factor that takes the surroundings also into account. In such an approach, a CAD software, such as SketchUp, will be used. In the software, after choosing the necessary location of the PV system, a comprehensive modeling of the surrounding landscape along with the PV system is carried out. For example, the figure shown here is a 3D model created in SketchUp for a certain location inside the TU Delft campus. Once the PV system and the surrounding environment is modeled, a plugin called LSS Chronolux can be used to calculate the Skyview factor for the modeled landscape. With this method, for the above location in TU Delft, the Skyview factor of the PV system was found to be 0.61. This is obtained after considering both the tilt angle and the surroundings of the PV system. For comparison, when the same PV system was placed in a free horizon scenario, its corresponding Skyview factor obtained through the equation approach was found to be 0.82. This value is 34% higher than the value obtained using the CAD-enabled approach. Thus, the Skyview factor that is calculated with both the tilt angle and the surroundings taken into account will be smaller than the Skyview factor based only on the tilt angle. The following figure gives an indication of the variation of the Skyview factor versus the tilt angle of the PV module for both free horizon and an arbitrary complex horizon scenario. The blue region in the figure represents the part of the sky blocked due to the tilt angle only. That is when the PV system is placed in a free horizon. Indeed, we can see that when the tilt angle is 0, the Skyview factor is maximum, while when the tilt angle is 90 degrees, the Skyview factor becomes merely 0.5. However, if we also consider the buildings and all the objects surrounding the PV surface, we obtain a much lower Skyview factor. The orange region in the figure represents the part of the sky blocked by the surrounding environment. Finally, the green region is the fraction of the sky that is still visible to the PV system. By using the CAD-enabled approach, a more realistic calculation of the sky view factor can be determined. Apart from this, the CAD approach is also advantageous when PV systems consist of custom-made PV modules, such as the infotainment spot shown in this figure. You may notice that the PV module in the system is curved, unlike the flat standard-shaped PV modules. For such a PV system, the CAD approach is a flexible method to simulate its sky view factor parameter. To recap, in this video, first you learned about the importance of sky view factor in irradiance modeling. It is an important parameter that is used in calculation of both diffuse and albedo components of the irradiance. Moreover, when a PV system is designed for a free horizon scenario, the sky view factor depends only on the tilt angle of the PV module, and it is obtained by using this equation. When a more complex horizon is considered, the sky view factor depends on both the tilt angle and the surrounding environment. For this, we use the CAD-enabled approach that uses the SketchUp software in determining the sky view factor.